Today we're going to be talking about ionic bonding. And so ionic bonding, what are we doing? We're stealing or giving electrons away, right? So it depends on what you are. So if you're a nonmetal, like chlorine over here, you're going to steal electrons from your metal, lithium over here. Lithium's going to give its electrons away. So how do we know what to do? If you look at the periodic table of elements, what you're going to find is lithium has an atomic number of 3. That means it has 3 protons. We're going to put the number 3 right here and say lithium. What does that mean? Well, it has 3 protons. It must have 3 electrons. And so we're going to have our first shell. Atoms, they start filling up the shell from the bottom to the top. The low shell fills up first, and that can hold 2 electrons. The next shell can hold 8, and the last shell can hold a total of 8 electrons. We're going to put our 2 electrons right here. Now, we're going to go on to our second shell. This shell can hold a total of 8 electrons. But, if you look over here, we only have 3 electrons, right? And so this is maxed out, 2 out of 2, but this can only has 1 electron, but that thing can hold 8. In order for this atom to be happy, it has to either be completely full or completely empty. This atom is not happy with this shell. Now, the options is it can give away electrons, steal electrons, or share electrons, or do nothing. Well, doing nothing is an option, right? We're not happy with the way things are. If we stole 7 electrons, we would have 7 more electrons than protons, and so we'd have a -7 charge. Realistically, the charges allowed are 2, 1, 0, -1, or -2, right? So if we stole 7 electrons, we'd have a -7 charge. That's not okay. And so we're not going to be okay with stealing 7 electrons. But we can give away an electron, and we only have a +1 charge. Let's look at chlorine over here. So if we look at the periodic table of elements, we see chlorine has an atomic number of 17. That means it has 17 protons in its nucleus right here. So we're going to put chlorine 17 to show that, hey, this is chlorine and it has 17 protons. Now, unless we state otherwise, the number of protons is going to be equal to the number of electrons. So we got 17 electrons, and as I said earlier, we're going to be able to fit 2 in this innermost shell. 17 minus 2 is 15. Okay, we got a problem here. What are we going to do with those 15 extra electrons? We can't put them in this shell, so we're going to put it in our next shell. That can hold a total of 8 electrons. We have 2 plus 8 is going to be a total of 10. So we got 10 of the 17 electrons accounted for. Well, what are we going to do with those extra 7 electrons? We're going to put them in the next shell, and that shell can hold a total of 8 electrons. As you can see, I got my 7 electrons here. This shell can hold a total of 8, but I only have 7 to put in there. So I could share electrons with somebody and get up to 8 here, or I could steal an electron from somebody else, and I would get up to 8 there. I could give all 7 of these away, and I would have 0. This shell would be completely empty. The problem with that is I would have a charge of +7. That's not allowed. I'm only allowed a charge of plus or minus 2. So as high as +2 or as low as -2. +7 is a lot higher than that. So what I'm going to do is I'm going to steal an electron from lithium over here, and that will give me a charge of -1, and that's going to be okay. What happened here? Well, I gave my electron from my lithium to my chlorine, and that is going to create a charge of -1 for my chlorine. That's going to create a charge of +1 for my lithium, right? These are now ions. What happens over here is this chlorine becomes an anion. The way I like to remember it is N, I pretend this is like a crossword puzzle, and so I got the word negative coming off the N, a negative ion. And so if you could do that, it really seems to help it stick. Well, it does for me at least. This over here is what's called a cation. With the word cation, I pretend the T is kind of like a plus sign. And that helps me remember that a cation is positive. These 2 atoms kind of like to hang out with each other because they're opposite charges. Opposites attract. They break apart in water because the water molecules will surround it with the opposite charge. So for example, our lithium is going to be surrounded by the oxygen atoms because they're all negative. Our chlorine over here is going to be surrounded by the hydrogen atoms in our water molecule because they're all positive. And so that's why these things break apart in water. Now, they also do something called an electrolyte. Electrolytes move electricity. And it's because we got both a positive and a negative. And so we have all these positive negatives in water that allow the water to be able to move electricity. So let's do a couple of questions, see how much you learned. Let's say you have an atom and it has a proton number of 5. How many electrons does it have? So the answer is going to be 5. Remember, the number of protons is going to be equal to the number of electrons unless otherwise stated. Next question. How many electrons would we have in each shell if we had 5 protons? So the answer is, you're going to put 2 in this first shell, because that's all the more it can hold. The second shell can hold 8, but we don't have 8 electrons to put in there. So we only have 3 electrons that we can put in there. And so that's how that's going to work right there. Next question. Which would be a better strategy for this atom to do? To steal electrons or to give electrons away? Alright, so a better option would be for it to give its electrons away than for it to steal electrons. Why? Because if I stole 5 electrons, that's going to give me a charge of -5. Why? Because each electron is a -1. If I give 3 electrons away, that's going to give me a charge of +3. That's going to be a little bit of a trouble for this atom in terms of trying to be happy, because we usually don't like charges above +2 or below -3. Another question. Why do we care about ionic bonding in the first place? So the answer is this allows us to move electricity in our blood. It also helps us understand how different things are connected. So, for example, your salt, we got NaCl, it actually breaks down into a positive and a minus. And so because these are charged particles, we can only pee out so much negative before we have to start peeing out some positives, right? And so we actually have to have an ion balance in terms of what we pee out and sweat out. The other thing that becomes important is getting fluids or getting these. For example, let's say that my potassium level is low. Well, you can't just give me straight potassium. And so there has to be something attached to it. It might be potassium chloride. It might be potassium calcium right there. So this is going to become important in terms of a thing called an MEQ. What we do is when we give you an IV, we pretend that we're giving you straight potassium. And so we're saying, in a sense, how much potassium are you getting in this IV? And these ions are going to be important in terms of chemical reaction, how our body processes food and so on. That concludes today's episode. If you liked what you heard, be sure to click the subscribe and like button down below. And as always, if you have any questions, comments, concerns, or if there's any particular topic you'd like me to create a video on, let me know in the comments down below. All right, well, I look forward to seeing you on my next podcast.